is Lorna and I am a Science Ambassador. Welcome to Rockingham Science Fair.
I'm Charlotte and I'm a Science Ambassador, and here are our science principles. At Rockingham Junior and Infant School, we agree that science is cross-curricular, engaging and fun. Lessons are pupil-led and carefully planned, giving real-life context. The outside spaces and local areas are utilised to provide regular outdoor experiences. ICT is used to enhance learning experiences and collect data. Children are encouraged to be independent, ask questions and work collaboratively.
My name is Ali. I thought of a creative way to make the solar system out of glow sticks. This was a group effort, and I know the order of the planets. The order of the planets is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. Project is an elephant habitat, and they live in hot places. This is an Antarctic one, and it's about penguins. And I got the pencil and I got this on it and that and this, and it shows you all about penguins, so I thought that is wet. This is a life cycle of a bee. The start as an egg, then larva, then a pupa, and then a bee. These are my elephant facts.
Hello, my name is Sophie. I have made a sundial, then I tried it out at home. A sundial is a thing that tells the time of day when there is sunlight. This is because of the position of the sun in the sky.
The Year Sixes have been focusing on the topic World War One, so I decided, because lots of shells and craters have been dropped, I've decided to do a science project to see which ball can make the biggest crater.
Okay, so what balls did you use then?
For the smallest ball, I used a marble, then I used a power ball and a tennis ball.
And how did you make it fair?
I used a tape measure and measured how high the ball was for every time. So no matter how big or small the ball was, I made sure that it was at the same height every time. I then dropped them, first from 20 centimetres and then from a 40 centimetre height.
Okay, and what were your findings then, Ava?
The biggest ball had the biggest impact, as when it dropped, because it was bigger, it was heavier, so it went deeper.
For my experiment, I did why do we celebrate icy roads in winter? Research. As the temperature drops in winter, our roads become icy and dangerous. When it is below 4 degrees, water freezes to ice. The tires cannot grip on the ice, spreading salt on the roads causes it to mix with the ice, and the ice melts. If I test the car first without salt, I can see if it works. any different with salt. Toy car winter salts baking tray. Pressure, I filled a baking tray with water and put it in the freezer to freeze. The next day I got the frozen ice on the side. I put the car on the ice and then it was sliding all over. Next I put salt all over the ice and felt it and left it for 2 minutes. I put the car back onto the ice and it didn't move one slide. Results: ice without salt, the car never slid. Ice with not salt, the car slided off the ice. Conclusion: the salt causes the ice to start melting. The tires grip to the salt to the ice.
Well, Freya, that looks like you've worked really, really well. And I love your presentation, and you've even got a car on there. And that's a photograph of you, Freya, testing your results. That looks amazing, Freya. Well done.
So my science project is about a star's life and how it's born and until its death. So first is the stellar nebula. A stellar nebula is the birthplace of stars. It is made out of hydrogen, helium, space dust and plasma. This is 10,000 degrees Celsius on average and doesn't actually form the star. Then after this, the star will either be an average star or a massive star. An average star is just like our sun and is 5,000 degrees Celsius on average. It is made out of hydrogen and helium. Then we've got the massive star. A massive star is a star that's larger than 8 solar masses. It is made of hydrogen and helium. And then after the average star, it will turn into a red giant. Even though it increases its size a lot, it is only 2,000 degrees Celsius on average, a red star. This is when it's nearly died and turns into a white dwarf. And the red supergiant, this has more than 10 solar masses and is 2,000 degrees Celsius on average. This is nearly in a supernova. And then now, a planetary nebula. This is made of hydrogen, helium, space dust and plasma. Even though it is called a planetary nebula, it doesn't involve the planets. Soon this will become a white dwarf. Then we also have a supernova. A supernova is an explosion of a star turning into a black hole or a neutron star. It is 1 billion degrees Celsius on average and lasts 4 billion years. Then we have the white dwarf. The white dwarf is 100,000 degrees Celsius on average, and a teaspoon of this is 5.5 tons. Stars from 0.8 to 10 solar masses can turn into a white dwarf. Then we have the black hole. A black hole is an object sucking objects into it. This is 23 billion miles big, and our sun is 553,240th of a black hole. And then we have a neutron star. This is 1 million degrees Celsius on average and can live till 10 billion years. The size of one is 13 miles.
Lift it higher.
During our World War I topic, we've been learning about life in the trenches, and especially at night it was really dark in the trenches, so they would need a flashlight to read instructions from the commander and even letters home. So I decided to explore how a circuit makes a torch work. And a torch works by using a simple series circuit, and it comprises a source of electricity, or also known as a battery, a switch, a lamp, and a conducting material, or the body of the torch, and that configures one terminal series circuit. A terminal of a battery makes contact with the terminal on the base of the lamp.
Using a pipe and mirrors, I made a periscope. If you angle the mirror at 45-degree angles, when you look through the objects, you can see over the tall objects. I did a parachute investigation, compare the size of parachutes. I found out the larger the parachute, the slower it would make an object fall to the ground.
Science learning. Oh, wow. So my science project, what did you do on your science project, Maisie? You did all about magnets, yeah? Did you learn anything about magnets? What did you learn?
It went through all the things I used to.
Did it? What materials did you use?
Paper and
Cardboard? Brilliant. Wow. Do you want to read one of your boxes out, what you wrote? The one that says, is that procedure? Would you like to read that?
I got my magnet and placed it underneath each material. I placed the metal nut on top of the object to see if they stuck together through the material. I recorded my results.
Wow. And what results did you get?
That all of them moved through them.
Oh, it did. That's brilliant. Well, Maisie, I think that looks absolutely gorgeous. And you've set that out really, really nicely. Well done.
Changing states of matter. Experiment. To find out what happens when the water is frozen, to find out what happens when the water is boiled, what is needed? Pink glass, water, ice cube tray, freezer and kettle. The method. Pour half of the water into the ice cube tray and place it into the freezer for 3 to 4 hours. Pour the remainder of the water into the kettle and wait for it to boil. Results. Remove the ice cube tray from the freezer and find the water has turned into ice cubes. When the kettle reaches boiling point, it turns the water into steam. In conclusion, when the water is frozen, it turns to ice. When the water is boiled, it creates steam.
Oh, well done, Lily. That looks amazing. And you've got all your results at the bottom. Did you like doing your science experiment? Yes, well done.
Why does the moon appear to change shape? The moon appears to change shape because clouds move over it and make it look like it's disappearing and reappearing. The new moon is when you cannot see the moon whatsoever. This is a start of month of the moon. This is the waxing crescent. Waxing means getting bigger because it'll keep getting bigger. This is the first quarter. Don't know why it's called that, it's a half. This is the waxing gibbous. So it's almost full. And then this is the full moon. This is the biggest of them all. This is a waning gibbous. Waning means it's growing smaller, so it'll. Yeah. The last quarter is about half of the moon again, but it's different to the first quarter because it's getting smaller. And this is the waning crescent, the last phase till it goes back to a new moon.
Excellent.
What materials dissolve in water? I'm going to test different materials to see if they dissolve in cold water. I will make my test fair by using the same amount of water and materials. What I will need: 1 tablespoon of coffee, 1 tablespoon of sugar, 1 tablespoon of flour, 1 tablespoon of salt.
4 clear containers, 4 hands of water for each container, a spoon to put in the materials and into the containers. Prediction. Before I did my test, I predicted that the salt and the sugar would dissolve and the flour and coffee wouldn't dissolve. Instructions. First, I got 4 clear containers and then I added a tablespoon of each material. I was using them in separate containers and then I added 4 hands of cold water and then waited to see if the water dissolved and the materials dissolved. The sugar and the salt dissolved straight away. The coffee took a little longer but it dissolved. The flour took the longest to dissolve. It did not dissolve fully. Conclusion. All the materials did dissolve using cold water, but I think the coffee and the flour would dissolve quicker in hot water.
Can you show us your learning then, Emmy? Oh wow, now this is lovely. Oh wow, well done. So is that everything you tested, Emmy?
Yeah.
And all your predictions? Wow, did you enjoy doing your science experiment? Yeah. Well done, it looks lovely. Off you go.
This bit says lines. What is this? It says what is a group of lines, a family of lines called?
And it's called
Pride.
Superstar. Can you tell me how fast can a lion run?
A lion can run as 50 miles per hour.
Super, but can they run at 50 miles an hour for a long time?
No,
No, not for very long. Why not?
because they get tired.
They do get tired. So can you tell me, where do they live, Thomas?
In Africa,
In Africa. Is that nearby or is that a long, long way away?
I think it's a long way.
It is, it's a very long way away. How many lions live in a pride, Thomas?
Which one's that one?
That's that one, good boy. What's the number?
40.
Super, 40 lions. Can you tell me how you made it? How did you make this?
My daddy printed these.
The pictures off.
Yeah, and then he printed this, but I drawed it, and he printed this picture, but I drawed it.
You coloured it in.
Yeah, I painted
Super.
it actually.
Oh,
And
painting.
painted that too.
Oh my goodness, that's creative.
These are plastic trees from in the sandpit and plastic rocks.
And you've
from the
used real
sandpit.
sand, haven't you, in yours?
From the sandpit.
It's super. I think you've done such an amazing job, Thomas. I'm very, very impressed.
You know, I made it because when this came, there's a box inside the boxes.
Oh my goodness.
Then he used it, so he cut out this bit, and then we made this bit of cardboard and writing lines. Then we put then
You did all of your facts.
yeah, and then things too.
Super. Let's have a quick look at it then. Let's keep it still. Let's have a really good look at it. Super. Give me a big smile. Good boy. It's amazing.
Here I have seen what dissolved in water. Prediction. I will be testing salt, pepper, coffee and sugar. I predict that all the materials will dissolve. Method. First put 200 milliliters of hot water in each cup. Then take 1 teaspoon of a material and put it in one of the cups. Stir for 10 seconds. Repeat for the other materials. Conclusion. From this experiment, I found out that pepper doesn't dissolve like I thought it would do.
Excellent, Holly. Can we have a look? Wow. And some lovely drawings at the bottom. And you've also got your results. Well done, Holly. That looks lovely. All about your creation.
A butterfly starts with the egg, then it turns into a caterpillar, then it goes in a cocoon and it turns out as a butterfly.
Super. So a cocoon is called a what? What does that word say there? It's called a... Can you remember? It's called a pupa.
Pupa.
Super. And how did you make this, Myla? What did you do?
I put it in a cardboard box, then cut it a little bit of paper, then put in more paper all around it.
And did you research your facts using the internet? Oh, and did you enjoy doing it, Myla?
Yeah, and I have a box of decorations so I could use these built for some decorations.
Oh, to make it really pretty. Let's have a little look at it then. Wowee, it's beautiful.
This one's dragged, this one's maple.
Super.
The other one's called flower and winning.
Lovely. Can you tell me what happens in the life cycle of a chicken?
It starts with an egg, a chick, and then a chicken.
Oh my goodness, super. And what do you like it best like? Do you like it best as an egg or as a chick or as a chicken?
Chick because it's easy to pick on.
This experiment, it's friction, equipment, what I need, medium-sized plastic bottle, a pencil, a funeral, rice flour and pasta. To make it fair, I will make sure it is a fair experiment by using the same bottle each time. I will fill the bottle up to the top. I will use the same pencil and put it in the same amount. I will only change the contents inside. Production. I think the pasta and rice will work, but the flour will be too soft for the pencil to grip. Result. I was able to lift the bottle using only a pencil when the bottle was filled with rice.
Conclusion. It's fine. Carry on reading us.
I had found out for friction to work, the contents of the bottle have to be hard like rice grains. They also have to be the right shape so that there are no air bubbles. There won't be enough friction if there are air bubbles.
That is excellent, Marnie. But yeah, would you like to show it us? Wow. Did you learn a lot doing this experiment, Marnie?
Yeah.
Yeah, and I love how you've done your prediction, your result, your conclusion. You set it out exactly like a science experiment. Well done, Marnie. That's gorgeous.
What would the most effective way of carrying food to the front line be? In World War I, supplies were scarce and limited because of the ongoing war, and soldiers had to live off the food that they could get, so they needed to transport it quickly and safely. And I designed a container to keep the food warm and safe, basically. And I needed the container to be strong enough to withstand being in the trenches and to hold the food and warm water and not have any leakages, to keep the food warm and not contaminated, to be safe to eat out of after being in the trenches for a while, and to be strong enough to not break from impact. And from my experiment that I was going to do, the aims were to get a better understanding of what materials keep heat better than others, to write a detailed hypothesis and conclusion, to be able to compare my hypothesis and conclusion to see more differences, and to document the experiment well. This was my design that I did. It's not very detailed, but basically I did handles and large place where to keep the food, and then hot water at the bottom to keep the food warm. And the experiment I was going to do was I've got 4 different containers, and I poured the same amount of water into these containers, like boiling water, and I timed how long it took them to cool down. And this is how long I thought it was going to take each container, and this is how long my family thought it was going to take, and how long, how quick they thought they were going to cool down, how slow, and that was what actually, how long it actually took.
So were you right in the beginning then, Layla?
No, I was way off.
You were way off.
Yeah.
But did you prove something during the experiment though?
Yeah, I proved that it took a very long time for it to cool down.
Yeah.
My science project was about what dissolves or didn't. Salt, sugar and flour. I did salt, sugar, flour and ketchup. The results were salt did, sugar did, but flour and ketchup didn't. I put the same amount of tap water into a glass each time. I measured 5 millilitres of each substance. I tipped it into the glass. I stirred for 10 seconds to see if each substance dissolved.
Well done, Amelia. Can we look? Wow. So you got all your materials, your procedure, your results, your conclusion. Did you enjoy doing your science experiment?
Yeah.
Yeah. Right. Well done.
My experiment I did about grit. Although it's called grit, what is used on the roads is actually rock salt. This lowers the freezing point of water on the road surface and stops ice forming. It also causes existing ice or snow to melt. Gritting lorries are used to spread rock salt on the roads in the cold months. They come out more than once a day, especially in the snow, because as each snowflake falls it makes the roads cold again and get icy.
Oh, let's have a look then, Noah. Wow, have you drawn that yourself?
Yeah.
That is amazing. Oh, this is really, really nice. And you set it out really nicely, look, with all your different paragraphs. Oh, that's lovely, Noah. Were you very busy?
Yeah.
Yeah, you've been very busy. That looks really good. Well done.
Because of our World War I topic, we've been learning about the different forces that we used, and the Navy is one of them. And they used periscopes in World War I. So my objective was to learn about how does a periscope work. How do we see through a periscope? We see through a periscope by a source of light hitting our eyes. Inside the periscope, there are 2 mirrors, and the light catches the first mirror at a 45-degree angle. Then the light reflects onto the other mirror, and the light projects through the top transparent part and hits the object, and that is what you can see. How does light travel through the periscope for it to work? Light travels in lines, and if it hits an object, that is what you can see. In the periscope, there are mirrors, and the mirrors reflect light. Who invented the periscope? In 1854, Hippolyte Mary Davy invented the first naval periscope, consisting of a vertical tube with 2 small fixed mirrors at each end at a 45-degree angle. Periscopes are still used around the globe today. Which climate do we use periscopes in? Periscopes are used underwater in submarines. They are most commonly used in the Navy to spot enemy ships and see icebergs. How does a periscope work? In a periscope, light from an object strikes at the top mirror at a 45-degree angle, then bounces off at the same angle. This sends light directly down the tube and onto the lower mirror. This mirror is also at a 45-degree angle and reflects light directly into your eye. And it's finished.
For my science experiment, I did magnets. What are magnets? Magnets come in all different shapes and sizes. Here are a few of them. Horseshoe, ring, bar, rods. Magnets have different strengths too. Some are powerful enough to pick a car off the ground. I found all the materials stuck to the magnet and the material did not stick to the magnet.
Let's have a look then, Lexi. Oh, that looks lovely. So you wrote all about magnets and you wrote your purpose and what your results were and your evaluation. Can you tell us what materials did stick to the magnets?
Paperclip stuck to the magnet, pen didn't, the screwdriver stuck to the magnet, the box didn't, the fork did, the plastic spoon did, the coin did, the glasses did, and the nomination bracelet did.
Wow, well, you've got some lovely results, haven't you? Can we have a look at it one more time? And there's a lot of pictures, Lexi, of you doing the experiment, testing all the different materials. That's gorgeous, Lexi. Well done.
Good morning.
Good morning.
Right, so we're going to do a little experiment this morning, yeah? And I've not told you what's going to happen, so you've got to use your brains, okay? So, the pieces of tissue that I've just given you, where are they? I need you to put them over each of the tubs. Can you do that? So, no, half in, half out, look what like this. So we're going to put half in that side, half in that side. Can you do that with that one?
Yeah.
Half in there, half in there. Good. Keep going. Half in there, half in there. Make sure it reaches. It won't work. That's it. That's it. Good. Keep going.
This is freaking.
Last one.
Oh my god.
Is it in?
Yeah, perfect.
Last one. Is it in? Yeah. Half in the water, half in the other one. Do it? Right. What do you think is going to happen?
I think they're going to change colour.
What do you think is going to change colour?
The tissues.
The tissues, yeah, they probably will change colour.
They're wet.
They are wet. Any other predictions? Do you think anything else is going to happen? So we've waited all day, haven't we?
Yeah.
For this experiment to work. And do you want to explain what's happened?
Well, what's happened is the food colouring and the paper towel, or the food colouring is like a flower on the ground. This is like the ground, the water, and this is like the flower, but instead it's a paper towel and food colouring. What's happened is this is like a flower and this is like the ground. And
yeah, you're doing well. And it's sucked up.
It sucked up the water.
Yeah.
Like this is the water and that's the flower.
Yeah.
It sucked up the water from the ground and it's moved it into the next pot.
Yeah.
And this one has done the same thing. It's just the food colouring has gone up the paper towel and down like a slide into the other tub.
Yeah.
And it carries on doing the same.
So, all these primary colours that we had, and these tubs in the middle, they was empty, weren't they?
The secondary.
Yeah, and the water has travelled up and into the empty tub, and it's made a secondary colour. Yeah, so we've got purple, and it was greener earlier, and I don't know why it's gone more blue. And then an orangey colour. So that's what's happened. And you remember what we called it? It was called capillary action, which means the ability of liquid to defy gravity.
The objective of my science project was to test different size parachutes to see how changes in size of parachutes affect the flying.
So what was your hypothesis?
My hypothesis was the small surface area of the parachute will mean the skydiver will land on the ground quicker than a larger surface area parachute.
Because there will be less air resistance.
Okay. And how did you carry it out?
I carried it out, so it was every parachute was a different size to make it more fair. So there was a 10 centimetre one, a 20 centimetre one, and a 30 centimetre one.
Did you use the same material?
Yeah, we used the same material for every parachute to make it a more fair test.
Okay, so tell me about the results then.
The results, the first parachute, which was the smallest, had the slower, it was faster than the big one. So resulting in the first time trial was 0.40 seconds, the second time trial was 0.62 seconds, and the third one was 0.62 seconds.
And what did you do in the end column, Jacob?
In the end column, we did the average time, and the average time for the first parachute was 0.55 seconds. The second parachute, which one was a medium, was 1.23 seconds. And for the first trial. For the second trial was 1.11 seconds. For the third was 0.99, making an average of 1.11 seconds. The third one, which was the biggest, the first time trial was 1.47 seconds. The second one was 1.33 seconds. The third one was 1.31 seconds, making an average time of 1.37.
So did you drop them from the different heights?
We dropped them from the same heights to make a more fair test.
Okay, and what was your conclusion then?
My conclusion was that the bigger the parachute, the slower it lands, but making a more safer landing than the first one. But the first one, being the quickest, would have been, if you used that parachute, it would have been gone quicker, but you would have probably broken your legs.
So we don't really want to be travelling by that first parachute then, do we?
So you wouldn't be wanting to travel by the first parachute.
Okay. Thank you, Jacob.
Thank you for watching our science fair video.